These are the notes for AP Calculus on the topic of integration by U substitution for definite integrals. So we've got the steps here for U substitution for definite integrals. Remember, definite integrals are when you have an integral that has a lower and upper limit. And many of the steps are very, very similar to U substitution for indefinite integrals, which we looked at previously. But there are a couple key differences. So if you forget what to do next, you can look back and refer back to these steps here to see what to do next. You can see, we'll see that the main extra step here that we have to do is step 5. We'll talk about what that means. All right, let's just jump into some examples and see how this works. Remember that with the U substitution, the goal is to take a more complicated integral and turn it into a simpler integral. So you can probably tell this integral way too complicated to integrate in this form. And we don't have anything that's where you the product rule for integration where you have two things multiplied together quite like this. So we have to use U substitution here. The question is, what would you say U equal to? And oftentimes it's a function inside. That's why I call it here, it's like the chain rule for integration in a sense, because the chain rule we use when we're taking the derivative when we have a function inside. So in this case, the only function inside is this 27 minus 19x squared is inside the cube root. So let's see what happens if we set 27 minus 19x squared equal to u. And remember, it could really be any letter other than the variable in here, x, when we use U substitution. So it could be W substitution or a different letter other than x. However, when you do this, for right now, I'm not going to write down this 0 and 1 as our lower and upper limits yet. I'll explain that part a little bit later in the problem. So let's start it off just like you would for an indefinite integral. Remember, we want to get this whole integral in terms of u. So now that allows us to write this as x, still is there, but now we can write this as the cube root of u. But remember, we don't want the dx in there, we want to get this whole integral in terms of u, so the way we get rid of the dx is by taking the derivative, in this case du dx, of whatever we set u equal to. The derivative of 27 is 0, the derivative of negative 19x squared, using the power rule, is negative 38x. And then solving that for dx, so if we multiply both sides by dx, the dx's cancel out here, you get du equals negative 38x dx. And then dividing by negative 38x gives us dx equals du over negative 38x. And then we can take that, and since that's what dx equals, substitute that in for dx. So we have times du over negative 38x. So you can see the x's reduce out there, which is what we want. We want the whole integral in terms of u, which now we have. So now, so far we've done everything identical to if this was an indefinite integral that doesn't have lower and upper limits. But now let's take a look at a key difference here. Let's think about what would happen if we wrote this from 0 to 1. So don't write this down in your notes, just kind of think about it. So if we did put 0 and 1, do you see what would not be correct about that definite integral? Well, remember, 0 to 1, those were the a to b values. Those were on the x-axis, right, the lower and upper limits. But notice there's no longer any x's in our integral. It's all in terms of u. So just like it wouldn't make sense to leave the dx there with this cube root of u because the variables wouldn't match up, the same thing is true if we leave it with 0 to 1. It's not technically correct because now our integral is in terms of u, but our lower and upper limits are still in terms of x. So the way we easily resolve that is by converting these to be in terms of u rather than in terms of x. So what we do is we just take them one at a time and substitute them in for x in our expression for u. So let's say we start with 1. So if you substitute in 1 for x, that'd be 27 minus 19 times 1 squared. Well, that's just 27 minus 19 gives you 8. So what we just found is when x equals 1, u is equal to 8. So our upper limit becomes 8. Now let's do the same thing for the lower limit of 0. If you substitute in 0 for x, you can see that wipes out the second term. We're just left with 27. So when x is 0, u is equal to 27, so our lower limit becomes 27. So now the whole integral is in terms of u, including the lower and upper limits. Now normally what you would do is you pull out the constant x, which is 1 over negative 38. However, you may have already noticed the lower and upper limits are in the non-standard order, right? Usually we'd have the 8 here and the 27 up there. So remember, we can flip them, and all that does is make a negative. But there's already a negative on the 38, so when you flip it, what the constant you could pull out would actually become a positive 1 over 38. So that would just change the sign. And then we could go from 8 to 27, the standard order, where we have the lower number here and the bigger number in the upper limit. But then to make it easier to integrate, we could rewrite this cube root of u as the same as u to the 1/3 times u. Now we've turned a more complicated integral with x in terms of into a simpler integral in terms of u. So now we can integrate. That 1 over 38 would just stay on the outside as a constant. When you integrate u to the 1/3, you get u to the 4/3. Add 1 to the exponent. And then dividing by 4/3 is the same as multiplying by the reciprocal, 3/4. Evaluated from 8 to 27. And then we can pull out the constant of 3/4 along with the 1 over 38. Well, 3 doesn't go into 38, so nothing reduces there. So 3 times 1, that's just going to be 3. And then 4 times 38, well, 4 times 30 is 120. 4 times 8 is 32. 120 plus 32 gives you 152. And then to make it easier to evaluate, we can rewrite this u to the 4/3 in radical form. It is the same as the cube root of u to the 4th. So now we've got 3 over 152. And then we can substitute in the upper limit first. So that becomes the cube root of 27 to the 4th. And then subtract what you get when you substitute in the lower limit. That becomes the cube root of 8 to the 4th. So we still have the 3 over 152 on the outside. And then the cube root of 27 is 3 to the 4th power is 81. Minus the cube root of 8 is 2 to the 4th power is 16. So we've got 3 over 152. 81 minus 16 is 65. Now let's see if that reduces at all. Well, 65 is made up of 5 times 13. Well, 5 doesn't go into 152, and neither does 13, so that does not reduce further. So we can just multiply the 65 times 3. Well, 60 times 3 is 180. 5 times 3 is 15. 180 plus 15 gives you 195 over, you have 152 in the number. So that's what this definite integral equals. Now notice there's something we didn't do on this problem that we did on u substitution problems for indefinite integrals. And that was on purpose. We did not substitute this u, 27 minus 19x squared, back in at the end of the problem. And the reason why we didn't was because we already converted the lower and upper limits to be in terms of u. So it wasn't necessary to plug that in. These were already in terms of u, so we could plug them directly into u. If we had actually plugged it in here, then it wouldn't have matched up again. Then these would have been in terms of u, and this would have been in terms of x. So you might wonder, well, couldn't we have just left this 0 to 1 and then plug that back in so everything's back in terms of x? Well, kind of yes and no. You could do that to get the final answer still correct. However, in the process, your steps would actually not be correct. Because what you would have there is at this step right here, these would be in terms of u and these would be in terms of x. And there may be a case on a problem on the AP test, they have had one in the past, where you would actually end up with a wrong answer, where if they don't work the problem out all the way, if you just, all your choices are just up to this step, and you have left that 0 to 1, that would actually be considered incorrect, because technically these have to be in terms of u. Plus, it actually makes it easier, I think, anyway. To convert these is a lot easier than having to plug this big expression back in for u and then plugging in the 0 and 1 tends to be a lot more complicated anyway. So because it's more accurate to do it this way, and because it tends to be easier, make sure you always, on u substitution for definite intervals, convert these to be in terms of u, the lower and upper limits, and then you won't have to substitute the u back in at the end of the problem. All right, let's look at a few more of these problems. So on the next one, again, there's no quotient rule for integration, so to make this simpler, let's try to use u substitution again. In this case, the only function inside is that x squared plus 4. So if we set u equal to x squared plus 4, this time, now that we know we have to do that, what you might want to do so you don't forget, because it's easy to forget if you don't do it right away, is to convert your lower and upper limits. Right now they're in terms of x, let's get them in terms of u. So if we substitute in the square root of 5 for x, that would be the square root of 5 squared plus 4. Well, square root of 5 squared is just 5, plus 4 gives you 9. So when x is equal to the square root of 5, u is equal to 9, so 9 becomes our new upper limit. And then let's substitute in 0. That would be 0 squared plus 4. Well, that's just 0 plus 4, which is 4. So when x is 0, u is equal to 4 becomes our new lower limit. Notice this time, it's still in the standard order, so there will be no need to flip it and make it the opposite sign this time. So let's see what we have left inside of our integral. This is called the integrand inside the integral. So we have x over, now we can just write it as the square root of u. But again, we want it all in terms of u, so we have to get rid of that dx. The way we do that, again, is by taking the derivative of what we set u equal to. Du dx here would be 2x. And then if we multiply both sides by dx, we get du equals 2x times dx. And then divide by the 2x, so dx equals du over 2x. And then substitute that in for dx right there. And then notice again what happens, which is what we want to happen. The x's reduce out, so it's all in terms of u. To make it simpler, this time there's a constant of 1/2 you could pull on the outside of the integral from 4 to 9. And then instead of 1 over the square root of u, remember there's no quotient rule for integration, so that's easier to integrate if we rewrite as u to the negative 1/2, because then we can use the power rule for integration on it. So we've got 1/2 as a constant on the outside. When you integrate u to the negative 1/2, you add 1 to the exponent, it becomes u to the positive 1/2. Divided by 1/2, the same as multiplying by 2, evaluated from 4 to 9. But notice when you pull the 2 out, times the 1/2, those cancel out, it just leaves you with 1. And then if you switch that back to radical form, u to the 1/2 is the same as the square root of u, evaluated from 4 to 9. So then you substitute in the upper limit first. So that's the square root of 9, minus, substitute in the lower limit, square root of 4. So you get 3 minus 2 gives you 1. All right, let's take a look at the next problem. On this one, you can see, if this was just cosine of t, we could integrate right away, but there's a function inside. In this case, the function inside the trig function is pi over 12t. So if we say u equal to pi over 12t, again, it's a definite integral, so that we don't forget, let's go ahead and first convert our lower and upper limits. Substitute in the 6 and the 4. And for t, these are right now in terms of t, we want it in terms of u. So if we substitute in 6 for t, that'd be pi over 12 times 6. But notice 6 goes into 12 twice, so that reduces to just be pi over 2. So when t is equal to 6, u is equal to pi over 2. So that becomes our new upper limit, pi over 2. And let's do the same thing for the lower limit of 4. So it'd be pi over 12 times 4. Well, 4 goes into 12 3 times, so that'd be pi over 3. So when u is equal to 4, when t is equal to 4, u is equal to pi over 3 becomes our new lower limit. And now we can rewrite this as the cosine of u. And then to get rid of the dt, we need it all in terms of u, so let's take the derivative of what we set u equal to. In this case, the derivative of pi over 12t, don't let that confuse you there. Pi over 12 is just a constant. So just like the derivative of 3t would be 3, the derivative of pi over 12t is just pi over 12. And remember, when your derivative there is a fraction, probably the easiest way to solve simply for dt, so we can replace it, is to just cross multiply. So when you have a fraction equal to a fraction, so we can say pi times dt equals 12 times du. And then to solve for dt, divide by the pi, so dt equals 12 du over pi. And we can substitute that in for dt right there. Then we've got a constant of 12 over pi we can pull on the outside. And now we've got an integral. Notice these are already in the right order. A third of a pi is less than half a pi, right? So all we're left with is cosine of u du. So now when you integrate that, we've got 12 over pi. When you integrate cosine of u, that just gives you sine of u. Remember, since our answer, when we find the answer, doesn't start with a c, it's positive, not negative. And then that's evaluated from pi over 3 to pi over 2. So we've got 12 over pi. Oops. And when we, usually what I do is just to remind myself, I plug it in after I substitute in, I use parentheses instead of a bracket there. So then we substitute in the upper limit first, so that'd be the sine of pi over 2, and then subtract what you get when you substitute in the lower limit of pi over 3. So we have 12 over pi, sine of pi over 2. Pi over 2 is right there on the unit circle. Sine is the y-coordinate, so that's equal to 1. Minus sine of pi over 3. That's like a 60-degree angle. Sine is the opposite over hypotenuse, so that'd be radical 3 over 2. So you could leave your answer like that. That'd be fine. That is correct. On free response, that'd be fine. But to make it a little simpler, what you could do is just distribute out that 12 over pi. So 12 over pi times 1 is just 12 over pi. And then minus, when you multiply 12 over pi times radical 3 over 2, notice the 3 goes into 12 6 times, so that'd be 6 radical 3, and we'd still have the pi left on the denominator. You could leave it like that, but since they already have a common denominator, it might be simpler to just make it a single fraction, 12 minus 6 square root of 3, all over pi. So once you get down to just constants here, just numbers they're all correct, it's just different ways of writing it. And sometimes with multiple choice questions, you may need to simplify to get it to match up with the answer. Okay, let's look at one more here. On this one, it might be a little trickier because to figure out what to say u equal to, you can see this is way too complicated to integrate like that. There's more than one possibility, because notice one function inside, both sine and cosine, even though they don't write the parentheses, it might be helpful to do that yourself, is you could think about setting u equal to 3x. But don't write that down, just let's think about what would happen. If we set u equal to 3x, then we could rewrite this sine of u times the square root of cosine of u plus 5. So you see how that would still be too complicated to integrate? So you could try it. Sometimes with u substitution, if you try something out, it doesn't work, you just have to try something else. That's what happens with integration. It's a little bit more of an art than derivatives, which if you just know the rules, you just apply those rules. Integration, there's different strategies you can use to integrate. If you try one technique and it doesn't work, try something else, and eventually, if you keep trying things, you'll find something that does work. And the more you do, the better you get at trying the right thing the first time. So 3x wouldn't work, but notice there's another function inside. This cosine of 3x plus 5 is inside the square root. So let's try that and set u equal to cosine of 3x plus 5. And now when you can, if you think about what's going to happen, you can foreshadow what's going to happen to see if it's going to work out. You can see the derivative of cosine of 3x would involve a sine of 3x, which will help us cancel out this sine of 3x here. So it's a definite integral, so let's substitute those in for x. So if we substitute in pi over 2, u equals the cosine. Well, pi over 2 times 3 becomes 3 pi over 2 plus 5. Well, cosine of 3 pi over 2, 3 pi over 2 is right here. Cosine is the x-coordinate. So cosine of 3 pi over 2 is 0 plus 5 gives you 5. So when x is pi over 2, u is equal to 5. That becomes our new upper limit. And then when you substitute in 0, well, 3 times 0 is just 0, so that becomes cosine of 0 plus 5. Oops. But cosine of 0, it is right there on the unit circle, is the x-coordinate, which is 1. So that's 1 plus 5 gives you 6. So when x is 0, u is equal to 6. Comes our new lower limit. And then we can rewrite this. We've got the sine of 3x. Now we set u equal to cosine of 3x plus 5, so that becomes the square root of u. And then we have to still replace the dx to get this all in terms of u. So when you take the derivative, du dx, well, derivative of cosine of 3x, since there's a function inside, that's going to require the chain rule. Remember, you start on the outside, the derivative of cosine. Since when you're taking a derivative, if the original problem starts with a c of a trig function, you know the answer is going to be negative, so it's going to be negative sine of 3x. But using the chain rule says we have to multiply it by the derivative of the inside function. Derivative of 3x is 3. And then the derivative of 5, it's a constant by itself, is 0. So then if we multiply both sides by dx, we get du equals, so we can pull this negative 3 on the out in front, so it'd be negative, so 3 out in front with a negative, I should say. So it'd be negative 3 sine of 3x, and then times dx. And then to solve for dx, just divide by the negative 3 sine of 3x. So that's what dx equals. And then we can substitute that in for dx right there. So du over negative 3 sine of 3x. So you see what simplifies then. You can see the sine of 3x is reduced out, which is what we want. Get it all in terms of u. We could pull out a negative 1/3 as a constant, but notice, again, our lower and upper limits are not in the standard order, so usually it'd be 5 to 6. So if we want to flip those, you can pull out just a positive 1/3. And then it becomes just 5 to 6. And notice all that's left is the square root of u. To make that easier to integrate, we can just write that as u to the 1/2 times du. So I've got 1/3. When you integrate u to the 1/2, that gives you u to the 3/2. Divided by 3/2, the same as multiplying by 2/3. Evaluated from 5 to 6. So, whoops. Before we do that, what we can do now to make it simpler, there's a constant we can pull out after we've integrated. The 2/3 times the 1/3 out in front gives you 2/9. And then if we simplify what's inside instead of u to the 3/2, it's the same as the square root of u cubed. Evaluated from 5 to 6. So we've got 2/9 on the outside. So substituting the upper limit first, 6, so that would be the square root of 6 cubed minus, substituting the lower limit, square root of 5 cubed. So we've got 2/9. And, oh, you could leave your answer like this. This is all just, at least this time they're not perfect squares. It's all just constants now, so that is correct. But let's pretend that this is a multiple choice question and none of the answers are written that way, even though that is the right answer. Well, square root of 3 cubed. Well, isn't that the same as the square root of 6 cubed, I should say. Isn't that the same as the square root of 6 times the square root of 6 times the square root of 6? But 2 of those just gives you the square root of 36. So that's just 6, and then there's 1 left over. So you could write that as 6 square root of 6. Minus, you can do the same thing with the 5s. Square root of 5 cubed, the same as square root of 5 times square root of 5 times the square root of 5. Again, 2 of those give you the square root of 25, or just 5. And there's 1 square root of 5 left over. So you could leave it like that, but let's say that still isn't match up with any of them, you could distribute this out. And if you want to leave it as a single fraction, you could distribute the 2 really, making it 12 radical 6 minus 10 radical 5 all over 9. Or you could split it into 2 fractions, but usually that's probably written as a single fraction like that. And that concludes the notes for AP Calculus on the topic of U substitution, integrating by U substitution for definite integrals.